Hi, welcome to another session of Circuits and Networks. In today's class, we are going to deal with transient analysis, especially the case which is involved with AC input. So this class we are going to treat as second class, and the concept we are going to treat as a level 2 concept. So there is a mathematics involved, which is involved with partial fractions. So let us see how to solve this particular problem. So the first case we are going to see when an RL circuit is applied to AC input, assuming that initially the resistance and inductor is not receiving any kind of input. Once the switch is closed, the source is going to get attached to RL circuit and current starts flowing. So the input voltage we are treating here as Vm sin omega t. So this will drive the current I of t, which is going to flow into this RL circuit. So when you apply KVL to this particular loop, you are going to get input is equal to the voltage drop across resistance and the drop across the inductor. So this equation is in the form of time domain specification. So we can change this time domain specification into frequency domain specification. Just wherever you have R, that has to be replaced by R, and the current it is changed as I of S. This is the Laplace value of current, which is shown in equation 1, and the equation 2 is the Laplace version of equation 1. Then inductor, you take this as L, and di by dt it becomes S, and I becomes I of S. So wherever you have L, it becomes SL. And the Laplace value of sin omega t is given by omega by s square plus omega square. So this is the important thing which you have to concentrate while transforming the time domain into frequency domain. So these are the two standard equations under time and frequency domain analysis. Now what we are going to do, we are going to take this I of s as common. So I of s is taken as common, and the equation is further modified like this. And further what we are going to do, we are taking the total denominator in the form of s and s square. Therefore this I of s becomes the Vm by s plus r by l multiplied with omega by l divided by s square plus omega square. Now this can be sorted out with the help of partial fractions. So the partial fractions will give you the value as k1 by s plus r by l plus k2s plus k3 whole divided by s square plus omega square. This type of partial fractions, it's advanced version of partial fraction conditions. So here you have s square term and you have here s term. So naturally we have to take care of this denominator power, that is s cube. So anyhow, this equation 3 contains s cube terms. So 3 constants comes in the partial fractions, so that has to be determined. So first we'll take the standard third equation and we'll take the partial fractions with Vm by L multiplied with omega. So it becomes Vm omega by L, which is equal to, you can see here I have cross multiplied these partial fractions. Then what I'm going to do, I'm going to take s is equal to minus r by l in equation 4, which makes what this equation 4 minus r by l makes this as 0 multiplied with this k2 k3, it also goes to 0. Then I'll be left over with k1. The k1 value here, it is obtained to be Vm omega l by r square plus omega square l square. So this we're treating as equation 5. Now clearly you observe equation 5, r square plus omega square l square, under root value is treated as impedance value. So the magnitude of impedance of RL circuit is replaced by Z. Hence equation 5 can be modified as Vm omega L by Z square. Now this is the value of K1. So similarly we need to find out the value of K2 and K3. For that, again we are going to consider equation 4, and we are going to reframe this values in terms of s square, s term and constant values. Now you can see the equation 4 is replaced as equation 6. Now I have s square term, I have s term. On the right hand side I have only the constant term. So I'm going to equate this equation. So from equation 6, the coefficients of s square will give you the value of k1 plus k2 equal to 0, which makes k2 equal to minus of k1, and this is given by equation 7. Similarly, from equation 6, equating the coefficients of s, we are going to get the value of k3, which is equal to Vm omega r by z square. Now I got the value of K1, K2 and K3, which is given by this equation 5, 7 and 8. So I'll replace this K1, K2, K3 by the actual values which is obtained in equation 5, 7 and 8. So I'm reframing this equation as equation 9 standard form. Now you can see I have the parameter and I have the Laplace inverse values which are obtained over here. So just apply Laplace inverse to this Laplace value. I'm going to get I of s is equal to I of t, right? This omega Vm omega L by z square will remain as it is, but the Laplace of 1 by s plus r by L will give you the value as e power minus r by Lt. Okay, now this becomes minus Vm by omega L by z square as it is. Now Laplace of this value is cos omega t, and Laplace value of omega by this value is nothing but sin omega t. Fine. So this equation can further be modified, which is given here. You can see I have taken Vm by z square common, so it becomes r sin omega t minus omega L cos omega t, and it becomes equation 10. Now from the equation 10, I am going to frame a triangle, which is known as impedance triangle, composing of r and omega L, which give the value of tan phi is as omega L by r. So sin phi and cos phi can be obtained as omega L by z and r by z respectively, which makes omega L equal to z sin phi and r equal to z cos phi. Fine. Now I'll take again this equation 10, and wherever I have r and omega L, I'll replace with sine term and cos terms. So you can see r is replaced by z cos phi and omega L is replaced by z sin phi. And again z is taken common, numerator z and denominator you have z square, one z goes. So this takes in this form. Now the standard trigonometric sine a minus b formula is sine a cos b minus sine b cos a. I'll apply to this particular value. So it will give you the value of I of t, which is equal to one exponential term and one oscillating term. So the exponential term is treated as the transient part and the oscillating term is taken as steady state part. So like this, I of t is obtained for series RL circuit. Similarly, we are going to apply the same concept for RC circuit when applied to AC. So once the switch is closed, current starts flowing. We know that Vs is equal to Vm sin omega t, and applying KVL to this loop, I'm going to get equation 1. So you can see the resistance drop is Ri and the capacitance is 1 by C integral I dt. Now take the Laplace value of equation 1. So Ri becomes Ri of s. 1 by C integral I dt becomes 1 by SC I of s, and sine term becomes omega by s square plus omega square. Now reframing this to get the value of I of s, so I'm going to frame the I of s value, which is shown in equation 3. You can see here we have Vm omega s by r whole divided by s plus 1 by rc s square plus omega square. Okay, now this can be changed to a partial fraction constants as k1, k2 and k3. As I told you, we have denominator s cube term, so naturally we have the three constants, arbitrary constants, and those arbitrary constants can be found out by first taking the equation 5 and substituting s is equal to minus 1 by rc, which makes the value of k1, here it is obtained to be minus Vm by omega c z square. So once the value of k1 is obtained, again we are going to take the equation 5 and we are going to replace in terms of s square and s term and constant term. With this we can get the value of k2 and the value of k3. You can see I have replaced this k3 in terms of z term, so it becomes Vm omega r by z square. Likewise, we have obtained the values of k1, k2, k3, and we are going to substitute in the standard I of s equation, that is equation 4. So wherever you have k1, k2, k3, I have replaced with k1, k2, k3 values. So you can see I have replaced this value and I have reframed the equation as 9 with RC. Now again applying inverse Laplace to this equation 9, which will give you the value of I of t, and that is obtained here with the standard impedance triangle of R and 1 by omega c. With this you can have the tan value, sine value and cos value, and the values of 1 by omega c can be replaced by z sine, r can be replaced by z cos. So I'm going to do that also. Again I'm going to get the I of t in terms of transient as well as steady state part. So this is how you need to solve the RL and RC circuit applied to AC. So it's a very important derivation, especially for triple students and ECE students. That's all for today's class. I hope you like this particular session. Please like this video, share among your friends, subscribe to this channel, and press the bell icon for the future notifications. Thank you.